So this video is going to discuss AC power. But before we actually get into AC power, I want to talk about the impedance triangle. So here we have a resistor of 3 ohms and an inductor of 4 ohms. And remember, the inductor has an angle of 90 degrees. And so if we were to draw this, we would have the resistor would have a value of 3 ohms. And then at the end of that, if we would draw the inductor, we would see that the inductor would go up at 4 ohms. And so therefore, the total impedance of this circuit, right? So the total impedance of this circuit, Z, total is equal to 3 ohms plus J 4 ohms. And so the magnitude of this is going to be 5 ohms with an angle of plus 53.1 degrees. Okay, so this is your standard 3, 4, 5 triangle, and this angle right here is the angle of that impedance, and so that's going to be 53.1 degrees there. And so if we wanted to work backwards to get the 3 ohms, right, the resistance, we would take Z, okay, so the value of the resistance would be Z times the cosine of the angle. Right, so that would be 5 ohms times the cosine of the 53.1 degrees. And if we were to calculate X of L, the reactance in the circuit, right, that would be Z times the cosine of this same angle. So this right here, the cosine is the adjacent, meaning that it's touching the angle. And this is the opposite angle, meaning that it's not touching. This leg here is not touching the angle, so it's opposite of it. All right, and so that's the sine. I'm sorry, I wrote cosine, but this is the sine of the angle theta. Okay, so it would be 5 ohms times the sine of this 53.1 degree angle. Okay, so we could kind of go back and forth. So this is the impedance triangle, okay, or the impedance diagram. All right, and the reason I'm showing you this is because when we talk about AC power, we have 3 types of power to discuss. We've already discussed quite a bit real power, right? So real power, P, is measured in watts. And real power is, we can calculate that as being I squared times R, or we can calculate it if we calculate our current I, okay, and by the way, let's go ahead and calculate the total current here, I, right, using Ohm's law is going to be E divided by Z total. And this is 50 ohms, or 50 volts, excuse me, that's 50 volts, and the impedance is 5 ohms. Okay, and so the current then it's going to be 50 divided by 5, so the current is going to be 10 amperes, right, at an angle of minus 53.1 degrees. Okay, so that's our current. So we could calculate the power in watts as being I squared R. That always works. Okay, so that's the safe way to do it. Now, if you wanted to calculate it using the voltage and the current, all right, it would be the voltage times the current, the magnitudes of these. Okay, so these are the absolute value or the magnitude values. So it'd be the magnitude of the voltage times the current times the cosine of this angle. In this case, it's 53.1 degrees. Okay, so this right here is what they refer to as the power factor. Okay, the power factor is the cosine of the angle. And if you take the cosine of 0 degrees, so if you had the cosine of 0 degrees, that is equal to 1, all right? And so if that was the case, then that means that the circuit has an effective value of nothing but resistance. Okay, so a cosine of 0 degrees means the power factor is 1, and you have total flow of power from your supply into your resistance, into your load resistance or whatever in there, meaning that if you do have an inductors and capacitors in there, they're canceling each other out. Okay, so that's total. A cosine of 0 degrees is equal to 1. On the other hand, if we take the cosine of 90 degrees, then the magnitude of that is 0. Okay, so if you had just an inductor or just a capacitor, you would be taking, the power factor would be, the angle would be 90 degrees, right? There's a 90-degree phase shift between your voltage and your current in the inductor or the capacitor, and therefore the power factor would be 0, meaning that you are not using any power. All right, so if we just had our simple voltage source here and it was feeding an inductor with no resistance at all right, we would still have current flow. But remember what happens here is this current charges up energy. It puts energy into the inductor during half the cycle. And then the other half of the cycle, it dumps that energy back out. And then, if this was the only thing in the circuit, it would actually end up just charging it up in the opposite direction, back and forth. And so inductors and capacitors don't actually use energy. What they do is they store energy or power. Okay, so inductors and capacitors store energy. So when we talk about power P and watts, we're talking about real power, power being used, power being converted. Okay, so it's being converted from electrical energy into thermal energy, or in the case of an electric motor, into mechanical motion. And so that mechanical motion is the energy that, and power is the instantaneous energy. Okay, so, so when we store energy, right, so over here we calculated the power P, all right, so what we have is we're going to use another symbol Q, okay, so we have P, Q, I think they just used that one because it was next in the alphabet, all right, but they use power, this up here is real power, P is real power, that's the power we're using. Q is what we call reactive power. Reactive power means it's the power or the energy that's being stored within the inductor or within the capacitor. And so reactive power, okay, is not measured in watts. Watts is reserved for true power. So Q represents what they call VARs, or we call it the units VARs. So remember, like power is volts times amps. Okay, so power is volts times amps. And that's the definition of a watt, voltage times amperes. But we only use the term watts for the real power being used. If it's energy being stored, we use the term VARs. So we put VARs in here. And so we're going to store energy into the inductor, into the magnetic field of the inductor, or the electric field of the capacitor, and that's going to be stored. So instead of being I squared R, well, that's going to be I squared times X, the reactance, right? Because it's reactive power. So VARs are volt amps reactive. That's what that R stands for, right? So real power is volts times amps. And the true unit for that, we use watts. But for Q, that's our reactive power, and that's stored volts amp reactive. Okay, so they actually just call that VARs. All right, and you could calculate that by using the magnitude of your voltage times the magnitude of the current times the sine of that angle. Okay, times the sine of that angle. So just like we had over here, we had the resistance was the total impedance times the cosine, and the reactance was the total impedance times the sine, okay? And so when we calculate the power, same thing here, all right? So we have we have P and Q. P is real power, Q is VARs, volt amp reactive. Now, if we looked at the impedance, right, here our impedance, we had Z is equal to R plus JX, right? So it's resistance plus the reactance. So when we talk about power, we have a total power. So we have something called total apparent power, and they use the symbol capital S for that. Total apparent power is capital S, and that's going to be the real power plus J times Q. Okay, so it's the real power plus the reactive power with its 90-degree phase angle, just like we had with the impedance. And so this is what they call total apparent power, and the units of that are volt amperes. Okay, just simply volt amperes. That's the units of apparent power. Okay, volt amperes. So volt amperes is a total apparent power. VARs is representing the energy being stored, right, which is I squared times the reactance. Okay, so it could be a negative there, or it could be a positive. Okay, and then the power is I squared R. All right, so now one way to calculate S then, okay, is, S is the total power, so theoretically that should be the voltage times the amperage. Okay, only what they, it should be amperage, it should be current, I, right? V times I. However, what they do is they put in the conjugate here. So the reason for that is because, remember, in our circuit here, okay, if we come back and look at the circuit, right, our inductance here was plus J4. Okay, so the inductance was plus J4, and so therefore the current had a minus 53-degree angle to it. And what they want to do is they want to keep power in line with the reactance. All right, and so we do this. This is the conjugate, which means you flip the sign of the current. Okay, so you take volts times amperes, right? So our amperes, so we had 50 volts times the 10 amperes. Okay, so 50 volts times 10 amperes at an angle. Remember, the voltage is at angle 0 degree. That's our reference. But then the current was at minus 53 degrees. Okay, but because we're taking the conjugate here, right? Because we're taking the conjugate, we're going to make this a plus sign now. All right, and so that's what the conjugate means. It means we're going to make this a plus in here, and then that way, all right, so this is going to give us 500 volt amperes at an angle of plus 53 degrees. And so if we were to draw that, right, we could draw real power. Real power here, P, is in this direction, right? And so that's going to be S times the cosine of the angle. Okay. And then we would have the Q, and again, the Q is going to be going in the same direction as X. And that's why we're doing this conjugate, so that we keep the Q in line with the reactance piece. Okay. And so that would be S times the sine of our angle. And so this is our total here. This is S. Okay, this is our total. And then this one here, of course, is going to be S times the sine of our angle theta, which is going to be 40 VARs, right? Because this is volt amp reactive. And this one down here is going to be S times the cosine of theta, which is going to be 30 watts. And this up here, our S, is going to be our apparent power, which is 500 volt amperes. All right, and this is that 53 degrees, 53.1 degrees. All right, and so this is what they refer to as the power triangle. And the power triangle okay. Okay, I'm sorry, this should have been 300 watts and 400 watts. Sorry about that. Okay, so the power triangle is identical to the impedance triangle up here, except for you're basically multiplying it times the square of your current, right? So it's your, right? This is our impedance here, which is 5 ohms at an angle of 53 degrees, right? Or 3 plus J4. And this here is basically your impedance triangle times I squared. Okay, so it's going to be 300 watts for real power, 400 VARs for reactive power, and the total apparent power is going to be 500 volt amperes. Okay. And so again, this is the power triangle. Let's say triangle up here. The power triangle. All right, so that is AC power. I guess I'll just say hi, Don.